Chapter 3 video series for EE 111 for Western Washington University. In the last two videos, we talked about how to combine resistors in series and parallel. We also talked about techniques to find unknowns. We can find the voltage across a particular resistor in a series combination of resistors using voltage divider. We can find the current through a particular resistor in a collection of parallel resistors using the current divider. And we talked a little bit about meters, ammeters and voltmeters being in series and parallel, and therefore what their equivalent internal resistances should be to minimize their impact on a circuit. In this portion of chapter 3, we're going to talk about kind of the last little loose ends of circuits that we need to cover before we really have a complete understanding of circuit analysis, circuit simplification. So the first thing we're going to talk about some strange circuit configuration, not strange, but some configurations we haven't really talked about yet. And this particular configuration is called a Wheatstone bridge. We have a collection of 4 resistors that are kind of form a diamond shape here. And a Wheatstone bridge is a very interesting circuit configuration where, based on these resistor values, as these resistor value changes, the currents through these different branches are going to change. They're going to sort of shift around. And a Wheatstone bridge is a particular configuration that generally we use where we have an unknown resistor, in this case Rx. Let me switch my color back here. And we have a controllable resistor here, R3. And the way we use a Wheatstone bridge is with this unknown resistor Rx in the circuit, we tune R3 until the current flowing through here is 0. So this current meter here, something I call a galvanometer, but it's for something that measures very small currents, and sometimes it's just something that tells you is there a current or is there not a current. The idea here is we tweak this resistor R3 until there's no current flow from this node to this node or vice versa, right? There's no current flow there. And what does that mean if there's no current flow? Well, if there's no current flow through here, and this meter it's a current meter, so it should have a small resistance, or as long as it doesn't have an infinite resistance. If there's no current flow, that also means that there's no voltage difference. So we tweak this resistor until the voltage difference between this node and this node is 0, as indicated by the fact that there's no current flowing through this low resistance meter that's connected between the two terminals. Now, this configuration, we're going to get into the math a little bit here in a sec. But why would we want to do this? Well, this is a handy way for us to measure an unknown resistance. In this case, we said this Rx is unknown. We don't know what it is. And measuring resistance, there's lots of ways to do it. There's not a lot of good ways to do it. So sometimes when I say, how would you measure resistance? Right now, think about a way to measure resistance. A lot of students say, we'd apply a voltage across the resistor and measure the current. That's great. That should be your go-to answer for Ohm's law, if you know Ohm's law. But the question is, that means that the accuracy of measuring our resistor is dependent on the accuracy of our voltage supply. And while sometimes we like to say you got a 10-volt voltage supply, how much do you think it costs to actually get a 10.000 volt voltage supply with no ripple, right? Like dead on smooth 10.00000 volts of voltage supply? That's going to be a very expensive voltage supply if you actually want something like that. And so for doing a measurement, unless we want to spend a lot for very precision things like exactly 10-volt voltage supplies, we need to have other ways of finding resistance, assuming we kind of have ugly supplies. And this is a way that we can do it. And this is not always just to find an unknown resistor. It's not always we have a mystery resistor and we need to find out what resistance it is. More commonly, this is we have a resistance which is a transducer. And we want to know what that resistance is because that resistance tells us what some other quantity is. I just used the term transducer. What do I mean by that? A transducer is a device that converts a signal from one domain to another. So you've probably encountered lots of different transducers, but people probably didn't call them a transducer probably because they didn't want to sound like they were trying to act really smart or something. I don't know. People don't use the term transducer normally when talking about things. Maybe, I don't know, maybe things have changed. Maybe it's a common term nowadays, but a transducer is basically just a fancy word for something that takes a signal in one domain. Could be thermal domain, could be light domain, could be magnetic domain, could be temperature domain, or I already said thermal. Thermal and temperature is another. I guess thermal is kind of the smart way of saying temperature, right? So So it takes a signal from one domain and converts it to another. And we're electrical engineers, so typically the domain we like to convert things into is the electrical domain. And there's quite a number of different sensors that convert chemical, temperature, radiation, magnetic strength into the electrical domain. And a lot of times resistance is the way they do it. For instance, there's a lot of sensors where they are a sort of a crushed up resistor. And when that resistor is pressurized, either by a chemical reaction that causes them to grow, or by moisture causing them to grow, or by a vibration compressing the crushed up resistive material, the resistance changes. Right? That's how a lot of older microphones work. That's how most sort of chemical sensors work, by having that chemical sort of absorb into something on the coating of a metal, which causes the metal to expand or contract or change its resistance accordingly. So quite often we have these transducers where they take a signal and they convert it into a resistance. And so for us, we want to have a circuit that's set up to where we can measure that resistance. And usually we don't want to have to just hook it up to a meter. We'd like to have a circuit, something in a more complicated circuit that we can use to determine what that resistance was, or determine changes in that resistance. And I've been talking a long time and I'm getting tired of hearing my own voice, but I'm just trying to kind of set the table for why we typically use these sorts of things, or where we typically use these sorts of things. All right, so analyzing this Wheatstone bridge, again, remember, we are assuming that this current flow is 0. We are assuming we have tuned this resistor R3 to the point that there's no current flow. What can we say about this? Well, say we have a current I1 here, I2 here, IX here, I3 here. We know that by Kirchhoff's current law, if there's no current flowing this way, then whatever current flows in here must also be the current that flows out there. So we know that I1 has to equal I3. Same thing goes on this side. If there's no current flow here, if we got 0 current flow here, then whatever I2 current flowed this way also has to flow this way. So we know that I2 equals IX. And we also know that in this case, if there's no current flow through a finite resistance, that means also there's no voltage drop across this. So we know that this voltage between here and here has to be the same as this voltage between here and here. And the same is true for the top side. This node is 1 voltage, and the voltage of this node and this node has to be the same. So this voltage drop and this voltage drop have to be identical to each other. So that's what's going on here as well. Now, we can do a little substitution. I'm going to kind of use this kind of pre-done slide thing here. We can substitute in that I1 there. Sorry, we can substitute in an I1 for that I3. We can substitute in an I2 for that IX. And that gives us this expression here. We can further take this expression and divide it by this equivalence expression. And when we divide it, we're going to get rid of the I1s on this side and the I2s on this side. And that gives us this expression, which we can then convert into a version that shows us our Rx. So now this is, again, we're tweaking a resistor R3 in order to find an unknown resistance Rx. And in this case, the expression Rx is the ratio R2 over R1 times R3, where R3 was that tunable resistor. Now, one thing to note about this is, where is V in this expression? V doesn't exist in this expression at all. So we found this resistance Rx without having to take into account the voltage across it at all. There had to be some voltage, right? There had to be some voltage. Otherwise, this whole, we tuned it till the current was 0 is going to be meaningless, because the current's going to be 0 to start with. So we have to have some voltage to make this thing kind of chooch in the first place. But once we have any voltage, it doesn't matter what that voltage is, this method of finding resistance gives us resistance as a function of other resistances. So it doesn't matter. So even if this voltage supply was 10.25 volts, even if this voltage supply was 10.279 volts and it was wiggling a whole bunch up and down, if we follow this process using a Wheatstone bridge, we can still accurately find resistance with whatever accuracy we can control the resistance of a tunable resistor. It's very powerful. This idea that we are essentially finding an unknown resistance in a way that rejects the voltage that's used to make the currents and voltages be produced in our circuit. It's very, 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 very powerful. Okay, so let's talk a little bit more about the Wheatstone bridge, as if I haven't talked enough about it, and then we'll do a quick example problem. So again, we've mentioned it's useful for finding resistance independent of the voltage supply. The voltage supply does not matter here. However, usually we're not using a Wheatstone bridge necessarily as this tune it until we get to the point where there's no current flow. More commonly, what we'll do is we'll use the Wheatstone bridge in the sense that it'll be configured with balanced resistors that are balanced at some nominal point. Let's say we're measuring temperature. We might have all of these resistors be 1 kilo ohm resistors, and we might have this resistor Rx be a thermistor, which is a resistor that's resistance changes with temperature. That is 1,000 ohms, 1 kilo ohm at 25 degrees C. So then this bridge is basically saying, at 25 degrees C, the voltage across these two terminals is going to be 0. But as that temperature goes above 25 or below 25, we'll actually start to produce a differential voltage. And if we start to produce a differential voltage, then that differential voltage will be slightly dependent on the accuracy of this V. But for the most part, if we're doing a sensor circuit, we're still substantially minimizing the impact of V on this signal. And a lot of times if we're doing a sensor, we really mostly care about this deviation from nominal. So for instance, a strain gauge is a very common transducer. A strain gauge converts deflection into resistor. It converts mechanical deflection. So flexure, something flexing, it converts that into resistance, and it works pretty simply. It's kind of a membrane that has a resistive material on top, and when you bend that membrane, the resistive material stretches out, and that causes the little particles to separate, and the more they separate, the more their resistance goes up. So it's a fairly simple operation. But these strain gauges are typically, these are installed in the scale in your bathroom has strain gauges that work like this. People build a bridge. Quite often they'll glue a strain gauge to the side of it to measure sort of how much the bridge is flexing as it's undergoing a load or as trucks go over it or whatever. But usually with those strain gauges, you want to know how much the material is deflecting from some nominal position. So if you have a steel beam, you would want the strain gauge to be a perfectly balanced bridge when the steel beam isn't at all flexed. And then you would have it so that when it flexes one way, this differential voltage is positive, and when it deflects the other way, this differential voltage is negative or goes in the other direction. Anyway, that's typically the way these are used. So in strain gauges, I just want to point out, people use two different forms of, if you ever use the wrong spelling, just say, yeah, either spelling works. There is people who do gauging a lot, do like to stress that there's a difference between these two spellings, but both spellings are used to refer to strain gauges. So just something to keep in mind, that some people, when you're actually doing measurement, some people like to use one version of the spelling and not the other. But I don't remember which version right now, so I'm a little on the spot, and I'm desperately trying not to say which version you're supposed to use for actually measuring quantity. So, okay, well, I said we are going to do an example. Whoop, we got to do this example here. All right, so the bridge in the circuit is balanced when R1 is 100, R2 is 1,000, and R3 is 150. The bridge is energized from a 5-volt DC source. What is the value of Rx? Well, luckily, we already know Rx equals R2 over R1 times R3. And it just so happened that these were numbered nicely the way our equation was set up. So always be careful. Sometimes these will be labeled, if this one were labeled R1 and this one was labeled R5 and this one was labeled R2, just be careful not to mix up your terminology here. But the biggest thing here is this doesn't matter. This 5-volt supply doesn't anywhere factor into this expression. So we have Rx equals, let's see, R2 is 1,000 divided by R1 was 100 times R3 is 150. So that should be 1.5K. 1.5 kilo ohms is Rx. Example problem complete. Okay. Remember that circuit I showed you before? I showed you in the last lecture series. I ended it by kind of saying, let's analyze this circuit. Oops, we can't analyze this circuit. So this is where we get to that. We can analyze the circuit. But a Wheatstone bridge is another example of a circuit that if we consider the model of a Wheatstone bridge where we take into account the resistance of that current meter in the middle, or that sort of middle resistor, a Wheatstone bridge is a circuit configuration that has no resistors in series and parallel. So look at it yourself. Spend some time looking at it. There's no resistor in here that's in series with any other resistor, and there's no resistor that's in parallel with any other resistor. And whenever we encounter that, when we encounter collections of resistors where nothing's in series or in parallel, it always means that we have one of two triplet resistor configurations known as the delta and Y circuit configurations. So the delta is shaped like a delta, which is a triangle, and the Y is shaped like a Y, which is a Y. And it should also be noted that these resistor configurations, the delta shape, we don't always draw resistors at weird angles, right? We don't always, sometimes we like to keep everything at 90-degree angles when we draw circuits. I very much prefer to draw circuits like that. And so it is possible to have a delta circuit that's drawn as a rectangle. So this is called a pi circuit, but you can just call it's a delta configuration too. It's just drawn like a pi, where you can see this bottom node C has just been stretched out. So all we did was we took this delta and we stretched out that bottom of the delta, and it kind of messes with my virtual background. You can see my green screen when I start doing this, so I'll try not to do it too much. I'm doing this in my shed. I'm in a shed right now. So we have, but it's sometimes called a pi, but I'm just trying to get you to sort of pay attention to these, that sometimes it might look like a rectangle, but really it's a triangle. It's a secret triangle here. And then this Y also, it's kind of shaped like a flux capacitor right here, but we can bend those top parts down and we can make it look like a T, and that's a T configuration. Okay, so now looking back at our Wheatstone bridge circuit, do you see any deltas in here? So pause the video, try to find two deltas and two Ys in this circuit. Obviously, they're going to be reusing resistors, but pause the video, try to find the deltas and Ys. Welcome back. So hopefully you found, let's do the delta. So hopefully you found one delta here, one delta circuit here, one delta circuit here, and one Y circuit here. And one Y circuit here. Okay. So yeah, there's lots of ways we can look at this circuit. We can kind of find a bunch of these, but the idea is that in order for us to simplify this circuit into an equivalent resistance, in order for us to reduce this collection of resistors, we are going to, at some point, have to convert from the deltas to the Ys or vice versa. And we can do that. We have a conversion we can do that will take a configuration, a delta configuration, and convert it to a Y, an equivalent Y configuration. Or it can take a Y configuration and convert it to an equivalent delta. So I'm going to skip for the purposes of this video the derivation of this. If you want, the book kind of glosses over the derivation too. There might be a homework problem that has you derive this, but it's doable. You can derive it. I mean, you can find anything with Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. So you can derive these equations using Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. But for now, I'm just going to give them to you. We're just going to give them, and the book kind of just gives them to you too. So if you have a delta with nodes labeled A, B, and C, you can convert it to a Y also with nodes A, B, and C using the following equations. R1 in this Y configuration is going to be RB times RC divided by RA plus RC plus RB. I just totally did this wrong, right? But that's basically this equation here. So we can find R1, this equivalent resistor, by applying this expression to the resistors in the delta. And then we can repeat it. We can repeat it for R2, we can repeat it for R3. I'm going to clean these up. So this is basically just plug and chug. There's not, so if we're not deriving this, it's basically just plug it into the formula. So what's the technique here? The technique to not messing this up is being very careful with your labels. Most of the time when students mess up a Delta-Wye configuration, it's because they're not clear with what's A, what's B, and what's C. And keep in mind, in your circuit's probably not going to have these deltas and Ys in such a nice, clean configuration that you can just, oh, clearly, that's the top of the triangle, that's the side of the triangle, that's this bottom side of the triangle. There's probably not going to be triangles, and there's certainly not going to be these Y shapes in your circuit. So it starts to become a little more abstract, and you need to be very careful with labeling. To this day, still, if I'm looking at a delta in a circuit and I want to convert it to a Y, or I'm looking at a Y in a circuit and I want to convert it to a delta, I will literally write A, B, and C. I will label those nodes before doing the conversion. So I will, wherever it is in my circuit, I will label the 3 nodes A, B, and C. And based on what A, B, and C is, you'll notice RC is the resistor opposite node C. And RA is a resistor opposite node A, and RB is a resistor opposite node B. But R1 is the resistor adjacent to A, R2 is a resistor adjacent to B, R3 is a resistor adjacent to C. Using the proper resistor is critical for making these equations actually work correctly. Okay, so we will do an example of that, but before that, I want to talk about a special case. What happens when these are balanced? What if we had a Y circuit? What if we had a Y circuit? Let's just do it like this. I'll say this one is 3, and this one is 3, and this one is 3. So that's a Y. And we can even go ahead and label these A, B, and C. I kind of stuck on my pen color as being purple, but I kind of like it. It's kind of nice. It goes with my shirt a little bit. A lilac, I guess. And what if we want to convert these to a delta? Well, let's look at the delta equations here. The delta equation says that RA is going to be, now luckily we say R1 equals R2 equals R3 in my example that I just pulled out of somewhere. These are all the same and they're all 3, so this equation is going to be 3 squared plus 3 squared plus 3 squared, so that's going to be 3 times 3 squared divided by 3. So it's going to be 3 times 3, it's going to be 9. And that's going to be true for all of them. And what you find is that in this case, where you have a balanced circuit, the delta configuration is always going to have resistor magnitudes that are triple the Y configuration. And conversely, the Y configuration will always have resistances that are 1/3 of the delta configuration. So it's just something to keep in mind that when it's balanced, when it's a balanced Delta-Wye, you can either multiply by 3 or divide by 3 to just immediately get the equivalent in the other direction. Don't mix the two up. Don't mix, be sure to note that if you're going from a Y to a delta, you're always going to multiply by 3. If you're going from a delta to a Y, you're always going to divide by 3 if they're balanced, only if they're balanced. Why do I kind of stress this a lot? Because when you're taking an exam in this class, there's only a limited amount of time and you got to get through these problems quick. And so it might happen that, I toss in, if I'm doing a Delta-Wye in there, it might be a balanced Delta-Wye so that it's faster for you. And it might also be a little faster for me when I'm grading it. It's a little bit easier for me to tell because there's a lot of paths to get to the top of the same mountain in this class. And when I grade your exams, I need to check what path you took for whichever way you went. And so it's a lot easier if they're balanced sometimes. It's not a guarantee. Some will be balanced, some will not be balanced. But if they are balanced, it's a quick conversion to multiply by 3 or divide by 3. Okay, let's do it. So let's look at this circuit and let's say, find the current through the 5 ohm resistor. Okay, so find the current through the 5 ohm resistor, and to do this, we're going to have to do a Delta-Wye. How do I know? Because it's the example problem after we talked about Delta-Wye. So finding the current through the 5 ohm resistor, that's fairly straightforward. That's going to be the current through this whole mess. So if I want to find the current through the 5 ohm, that's the same as the current through the 40 volt supply. I'm just going to have to find the equivalent resistance of this entire circuit here. Okay, so if I'm trying to find the equivalent resistance of the entire circuit, I'm going to have to start to take apart this Wheatstone bridge or Wheatstone bridge looking shape over here. So what I'm going to do is I'm just going to pick this top triangle. We got a nice little delta here. I'm just going to pick this triangle up here. And we're going to apply those equations we just talked about to do this conversion. And to apply these equations, I'm going to clean up all of this mess here. Okay. Okay, so first thing we got to do is we got to label these. Now you'll notice again, this is not the same looking delta, right? The delta here was an upside down triangle. The delta here is a sort of right side up triangle. I guess I could do the bottom side of the circuit if I want, but I don't. I'm going to do the top. So we got to pick labels for these. So I always do them numerically. So I'm just going to label this one A, B, C. Sorry, but I do them in alphanumerical order. So it's easier for me if it's clockwise A, B, C. I guess it's 3, so you can't really get them out of order. But you got to be consistent. So we label them A, B, and C. And what that means is that by these labels, this is now RA for the purposes of our equations. This is RC, and this is RB. Very important to keep that in mind. Okay, so let's go back and find out what these expressions have to be. So first of all, what we're trying to do is convert this into a Y circuit. So if we're trying to convert this into a Y, eventually it's going to be replaced with A, B, C, where this one is going to be R1, this one's going to be R2, this one's going to be R3. And so we'll once we solve for this, we're going to have to kind of insert that into our circuit, and I'll show that process here. But first of all, we got to get through some of these equations. Okay. So we're going from a delta to a Y. So we are going to use these equations here. So R1, now the first thing to note when I do these is the denominator here is the same for all of these. So before we start doing too much plugging in numbers, let's just get this one out of the way first. RA plus RB plus RC. So that's going to equal 25 plus 100 plus 125. That's going to equal 250. Perfect. Okay. Now let's go back to our equations. So R1 is going to be RB times RC. Divided by the sum of those, which was that 250. So RB is 100. RC is 125. And that's all divided by 250. So, I mean, looking at this, that it better be 50. I'm guessing. I mean, I'm not guessing. It better be 50. So 50 ohms for R1. R2 is RC RA. So RC was 125. RA was 25 divided by 250. So that's going to be 25 divided by 2, which is going to be, what happened? 17.5. And then lastly, we have R3 going, oops. Making it worse here. Oh, my shed that I told you I was in has got a motion sensor. It just cut the lights on me. You know what? That's fine. Okay. Okay, so now we're left with RA times RB. So this is RA times RB divided by 250. RA is 25. RB is 100 divided by 250. So that should be 10. Okay, so we now have this equivalent set of resistances here, which is R1 is 50, R2 is 17.5, and R3 is 10. Let's see if I left myself. I did leave myself some space to work. Perfect. So let's redraw this a little bit. So I'm gonna have to skip back and forth a little bit here. So we had first of all, this voltage supply drawn like this. So there is a video where I talk about this. I haven't posted it yet. There's a kind of a grab bag video where we talk about these a little bit. That's just another symbol for a voltage supply. Technically, that's a symbol for a battery. And technically, a battery refers to a collection of series electrochemical cells. But over time, that batteries, the symbol for a battery started to kind of just be used to describe essentially any voltage supply. And so it's fine too. We can also use a single cell. So a supply that looks like this, which is historically, that's a single electrochemical cell. A battery is multiple series electrochemical cells. That too, though, these are all just different ways of drawing a voltage supply. So I just noticed we might have shown them and talked about them, and I didn't talk about them yet. There is a video that kind of talks about it. I'll post it soon, but that's just a voltage supply, 40-volt voltage supply. So we had a 40-volt supply, we had a 5-ohm resistor, and now we got to insert that Y that we converted. So we had a 50 on top, a 10 here. I think it was 17.5. Okay, and then we had a 37.5. And then here we had, oh, my laptop is having trouble determining a finger. We had a 40. Okay, so now we can simplify this even more. Now we actually can simplify this now, because now we have a 17 in series with a 37.5 and a 10 in series with a 40. So now we can actually simplify this. So the 17 in series with a 37.5, that's going to be 17 plus 37.5, which, just doing it in my head, should be 55. So, and then the 40 and the 10 should be 50. So redrawing this, we should have and then this one was, is that right? No, it's not 17.5. Look at that. Hopefully you're yelling at me. 17.5, man, what was I doing? 12.5, 25 divided by 2 is 12.5. Not gonna, sometimes it's good in life. Sometimes you gotta just live with those mistakes. When you make them, you just gotta own them. I could go back and edit the video, but the shame will be reinforcement for me to not make this mistake next time. So 25 divided by 2, 12.5. Sorry for everybody who was yelling at punching your laptop screen as I was making this mistake. 12.5, which actually makes this a lot cleaner here. Look at that. The math is so much cleaner. So now we have a 50 in parallel with a 50, which is going to be 25. So we can redraw this one more time. Okay. And now, actually, we'll do it one more time. So now we have 5 plus 50 plus 25. It's going to be 80 ohms. So we can write this as an equivalent. So an equivalent 80 ohm resistor, 40 volts here. So this current I, by Ohm's law, I is equal to V over R. Okay, so 0.5 amps. And we know we had 0.5 amps flowing through this. That was the current through the 5 ohm. Now, normally we solve for the total current. We have to sort of unfold this thing. We have to kind of unravel this thing. And you know, I mean, that's just what we got to do. But in this case, finding the current through the 5 is fairly easy because the 5 is in series with the supply. So whatever current flowed through the supply also has to flow through the 5 volts, the 5 ohm resistor. But, and this is probably a better example for the types of problems you're going to get on the homework, we had an extra challenge, which is find the voltage across the 40 ohm resistor here. So one of the things, whenever we simplify a circuit, and we use these techniques that we've learned in chapter 3 to simplify a circuit, quite often we have this case where we've simplified a circuit, but now we have to go back. And we have to sort of unsimplify the circuit until we get back to the portion of the circuit that we were trying to find. And in this case, we have this 40 here that after this step, it's gone. Right? That 40, it's now combined with a 10, it's a 50. So we're gonna have to work our way back. We're gonna have to do circuit analysis on our going back here to the point where we can find something about this 40. We're gonna have to step back to the point where we can find this 40. There's several ways that we could do this. So for instance, we could find the voltage, we could use voltage divider to find the voltage across this 25. I'm gonna change, I'm starting to get messy here, so I'm gonna change to red. We could use voltage divider to find the voltage across this 25. We could apply that to this circuit drawn here. And then we know that 25 is here. So whatever this voltage was, that would be the voltage between here and here. And then we could do a voltage divider on this little section of our circuit, right? We know there's this many volts across these two resistors in series. So we could do a voltage divider to find the voltage across the 40. Alternatively, we could use current divider to find this. So we could say basically right now we know that there's 0.5 amps here. And we know that 0.5 amps, well, let's do it on this one. We know there's 0.5 amps here, and we know that gets split here. Some of it goes here and some of it goes here. But we have a known current, 0.5 amps, that is flowing into this parallel combination of a 50 and a 50. So we can use current divider to find how much of that current is flowing through this branch. Now it's fairly straight, because they're the same value, it's fairly straightforward here, but let's pretend it's not straightforward. Let's use current divider to find the current through this 50 ohm resistor here. So let's try to find this current here. So this current here, I50, is by current divider, is going to be the total current, which is 0.5 amps, times the equivalent resistance of this whole collection, which is 25, divided by the resistance of the branch, which is 50. And that equals 0.25 amps. Now, I want to stop and talk about a few things here. One of them is, a lot of people say, why didn't we have to deal with this? Why didn't we have to deal with that resistor here? I'm going to switch colors again I'm going to go with green. I haven't done enough green. So this is a really good question. And it seems weird that we just say, oh, there's 0.5 amps, but the 0.5 amp flows through the 50. So why don't we have to deal with that? Well, that 0.5 amp, it's kind of baked in that the 50 is in series with the 5, is in series with this collection here. So basically, the reason we don't care about the 50 is because we know that there's 0.5 amps flowing all the way through this here. So, I mean, we do care about the 50, but we already know the current through the 50. We know the current entering the 50 is 0.5 amps. We know the current exiting the 50 is 0.5 amps. paths. We don't care about that. What we care about is where it branches, where the current splits off. The current splits off right here. So part of that 50, part of that 0.5 goes here, part of that 0.5 goes here. This is my parallel, this is my current divider. This is my section of the circuit where I apply current divider. This is the section of my circuit where I have a known current flowing into a parallel collection of resistors. This 50 was not in parallel with those other 50s. That 50 is not in parallel. It's not part of my current divider circuit. It's not part of my, I don't use the current divider formula with it. I have a known current, 0.5 amps, flowing into a parallel collection of circuits, parallel collection of resistors, trying to find the unknown current through one of them. It's only this little section, and it's only the known current flowing into that section that I care about. So in this case, I knew I had 0.5 amps flowing into it. I knew the equivalent resistance of those resistors in parallel was 25, and I knew that the resistance of my branch in question was 50. So that's all I need to focus on here to find that I had 0.25 amps flowing through that. So now that I know I have 0.25 amps flowing through that 50, that means that I had 0.25 amps flowing through that whole branch here, right? This 10 and the 40 are in series. I know, sorry, I just bumped the mic. The 10 and the 40 are in series. We know that there was 0.25 amps flowing through it. So because they're in series, the current through them is the same. It's 0.25 amps. And so if I have 0.25 amps flowing through the 10 and the 40, then the voltage across the 40 here, by Ohm's law, the voltage across the 40 is going to be I times R, which is going to be 0.25 times 40, which is going to be 10 volts. Okay. That might be a little confusing. This process we went through might be a little confusing. You might kind of be scratching your head about, well, why did you just treat that as that? Why did you just, and to a certain extent, I apologize, because I've found that I'm best teaching this class. The closer I am to what was going through my head when I first learned this stuff, the better I am at teaching this class. So at a certain point in time, the longer I've been doing this, the more I start to gloss over things. But the homeworks are really important here. So the homeworks are really important to give you a chance to sort of go through a problem you haven't seen before, to try to sort of figure out in your own head how to do it one way, how to do it another way, to kind of sort of make some mistakes, to find out what mistakes you made. I personally like to always have the solutions manual available to you. I know most of you have Chegg or whatever. You're able to get the solutions one way or another. So I do have the solutions manual posted. And what I want you to do is, if you do a problem and you're struggling with the problem, that's a good thing, right? It's okay to sort of be confused or to have a question, but focus on where that question is. So note, if you're stumped by something, remember where you were stumped there. And don't immediately jump to the book. Struggle with it for a sec. Try to figure it out on your own. And if you can't, then that's a great time to maybe check the solutions manual, see if it helps. Maybe contact me during office hours. Contact Shichen during office hours if he's still teaching this class. And I don't know, or it might not be me teaching the class, you know. So who knows? It could be any of the other faculty teaching this class next year, or whenever you're watching this video, if you're not watching it in 2020. But you know, it's a good time. Struggle with the problem. The homework problems are there to help sort of instill some of these techniques, to help you kind of understand some of these. I understand after I do these examples and I look at this screen, it's covered with mess, and I understand this might be confusing, and I'm probably skipping over some things, but the homework problems really help with this. And find out where you're having, if you're confused by something, it's totally normal. This is not intuitive stuff. It's a little strange. If you're having an issue with a certain portion, remember what that portion is. Come and talk to me in office hours. Come and ask for help. You know, check the solutions manual. Whatever you need to sort of to get past that. But also remember what the uncertainty you had was, and really try to understand how that uncertainty was resolved when you look at the solution or when we talk to you about the solution. So that's the best way to kind of really instill this stuff, to understand this stuff. But also, as a caveat, we're finishing chapter 3. Everything feels weird after chapter 3. Chapter 3 is when we have fully deconstructed the process of analyzing circuits. We have blown everything into disorder. We have thrown a million things at you: Delta-Wye, series, parallel, voltage divider, current divider, Ohm's law, Kirchhoff voltage law, Kirchhoff's current law. We've thrown all this stuff at you, and we've said, here's this big giant mess of tools that you can use to solve anything. We haven't actually added technique yet, though. And so if things are a mess in chapter 3 and you're like, I don't know how to start, I don't know where to start, I don't know why you decided to do that when you did that. I don't know what I should start to do to decide what to do when I do something. That's natural. We haven't talked about that yet. That chapter 3 is we're just throwing everything at the wall and seeing what sticks. And we're saying you can do everything with this, so good luck. And the homework, to a certain extent, it's good to go through that process. It's good to try to do it that way. But just keep in mind that there's light at the end of the tunnel. In chapter 4, we start to go over technique. So chapter 4, we say, here's the process you should follow to find a solution without going in too many circles, without beating your head against the wall, without sort of, crying alone while social distancing. I don't know. But basically, if it feels confusing and convoluted, chapter 4 cleans it up. Chapter 4 brings everything together. Although on the flip side, chapter 4 means we get more complicated circuits, but at least we'll have a technique when we're doing those circuits, because a lot of chapter 3, a lot of the homework problems you do in chapter 3, you're going to be feeling like, wow, like I don't know where to start. I don't know why. And you're going to feel lost in some of these sections, and that's okay. And we'll help unlost you in chapter 4. So until next time, thank you for watching.